Okay, I've already talked a little bit about the excess reactant. We've encountered it in some questions where it says, the other reactant is excess. And this is all about reactants. Notice it says limiting and excess reactants. The stuff on the left. Nothing about product. This is all about reactants. So for any manufacturing process, anywhere where you build something, whether it be molecules out of atoms and ions, or whether it's something made out of Lego, or whether it's a manufacturing plant that makes bikes or cars or anything, there will always be more than one piece that you got to put together. And in some cases, you might have some extra pieces when you're done. Like if you build anything out of IKEA, an IKEA thing. They do that on purpose. They'll give you an extra few bolts and nuts and things that if when you're putting it together and you drop it and it gets away, you've got an extra one. So when in any manufacturing process, there are extra pieces, we would say it's excess. We've got extra, okay? And when it comes to building molecules, if I have more than one reactant, so something like a synthesis or a double displacement or combustion, then one of those chemicals will be extra or excess, all right? So the extra one, the one that has extra, we call it the excess reactant. All right. The other one that runs out, we call it the limiting. So the other reactant that isn't extra is going to run out, and it will stop the manufacturing process. If you're in some kind of a factory that builds bicycles, and you've got all kinds of frames and handlebars and seats and wheels, and if you get to a point where some delivery hasn't been made to bring you those parts and you run out of wheels, then the whole process stops. Even though you've got extra of everything else, the one that runs out stops the process and you can't make any more. The same is true with chemicals, all right? You'll have one chemical that there's extra and the other one's going to run out, and then it's done because you have no more parts to make the product. So the limiting reactant is the thing that we're interested in the most because it's going to be what's used to find the product number. All right? Up to this point, that's why I've said to you, the other one is excess. Don't worry about it. So the number I gave you was the limiting, and you just calculated it. The only trick to this question is, I will give you two numbers at the beginning, and you got to pick or determine which one is limiting, which one's going to run out. Then you just do the problem again, okay? So we have to determine which one's limiting. Okay. So a little example on how to determine that, something that isn't chemical related. So, back in the 80s, when you played with Lego, you didn't have all of these fancy sets that allowed you to make the entire Death Star or perhaps Hogwarts or something cool. So you had to use your imagination. So when battling one's brother in a Lego war, you had to be very efficient at making fighter jets. And the easiest way to make fighter jets is to use two 2x4s like this and one 2x2 like this for the tail. And then you've got yourself a nice little possible X-wing fighter, if you imagine hard enough. If you wanted to make it really cool, you move the 2x2 back like this. And then that really flies a lot faster. That's a faster orientation. But to make a fighter jet, you need 4 2x4s and 1 2x2. So for each fighter jet, let me take that apart. So to make jets, to make some jets, the reaction is you need 2, now let's be creative, folks. Let's be creative here. 1, 2, 3, 4, 1, 2, 3, 4. You write this down. I'm not doing the, oh, I should do it on the smartboard because I'm recording it. To make some jets, so to make some jets, we need 2, oh, sorry, not 2 of them. What did I say? How many do we need? 4 of them. I'm not even building my own jets properly. You can't fly a jet with 2 2x4s. That's crazy. 4 2x4s. And I know you're not all as artistic as me, so it might not look so as good as mine, but that's okay. It's all right. You're learning. And we need 1 2x2. To make, now one year I did try to draw a 3-dimensional representation of a jet. It failed miserably because I'm not that good at being an artist. 1 jet. All right. And you can see I've got some Legos up here. So now I need some people to count up my Legos. Kelly, could you count these Legos for me, please? Get up and count them. Jenna, I need you to count the 2x4s for me. Now, you come on. This is participation. It's fun. Come on. I'm gonna. How many? What? You're no fun. Okay. 16. Hold on. Slow down. I got 16. Now, these essentially are entities. They're the individual pieces. If I knew what the mass of each brick was, I could weigh all the bricks and we could do some molar mass stuff. It's too much work. We're working in the line which we consider moles. So we're looking at our pieces line. So I'm down here, and what did we say, 16 2x4s? 16 2x4s. And what did we say here? It's 12. 12 2x2s. How many jets can I make? How many jets can I make? Yeah, what do you think, Charlie? I can make 4. How'd you get that? Okay. Yeah. Okay. So you need 4 here, but you got 12. Yeah. Excellent. That's exactly how we solve that problem. It is that easy. What Charlie did was he used the mole ratio, or the ratio of parts, to determine how much of the other one is needed. And then he quickly compared how much we have to how much we need, and figured out that we can only make 4. Excellent. That is exactly how to do it. And that's the way I'm going to write it down. So let's do it exactly like we would when we do a real problem with some chemicals. So I can go this way with the mole ratio. In this case, it's like a brick ratio. Same idea. In this case, this is what I have. So I'm going to put a little mark there to say that's what I have in reality. And I want to calculate how much I need. All right? And that's what I'm going to calculate with the ratio. So in one of the mole positions, I will have 2 numbers. One, how much I have, and the other, how much I need. And then I just have to use some logic to figure out if I have enough or I don't have enough. So to make it look official, 16 bricks divided by 4, that's going to tell me really how many I could make with the jet bricks. I'm going to put an X here divided by 1, right? Because I'm doing the same mole ratio like I've been doing. And therefore, X is going to be 16 divided by 4. And that tells me I need 4 2x2s, right? Which means I need 4. All right? Now the question then becomes, do I have more than I need? In this case, it's yes. If I have more than I need, then we will label this the excess reagent. Sorry, reactant. I say reagent because that's the way I was taught. A reagent is just a term for when we actually use a chemical in the laboratory. It's the same as reactant. So this is the excess reagent, and right away, now that we know this is the excess reagent, what does this automatically have to be? The limiting reactant. Once we know the limiting reactant, we will do a second question, and you don't have to change the color, but I'm going to just do it so we can see it, where we're going to use the limiting reactant to find the products. Then we do the problem just like we did. So it's kind of like we do the problem twice. We do it once to see how much is needed, we determine which is limiting, and then we do the problem. And because it's the same ratio, 4 to 1, just like this, we will make 4 jets. 4 jets will be made. Okay? All right? So, like I said, this is just an add-on. Let's do 2 examples, and then I let you work. Did you want to make the fighter jets as well? You want to put them together? No, you don't have to. Maybe later. Later. Well, you would have, if you were fighting against your brother in a war, you're throwing a lot of Legos across the room. They don't fly really that well. Yeah. But when you make them, you got to line them up nicely in a row, like on an aircraft carrier, right? So that they're ready to take off. Does that bother you?
Yes. Like, probably. Also, why are you
Keep writing the question. Don't be distracted by my Legos. Balanced chemical equation. Give it a shot. So go ahead, give a balanced chemical equation a shot there. Somebody have an attempt at it? What do you got? 2 to produce 2 MgO. Yes, excellent. 2 and 2 on the MgO. All right? Those aren't just stuck together. They're a 2 and a 2. So when doing one of these problems, I don't always say, A, determine the limiting reactant. Sometimes I just say, determine the mass of the product formed. So you've got to realize yourself that it's a limiting reactant problem, and I'll show you how you tell. Just like in any of our problems, we're going to write the information down underneath them. I have 6.73 grams of Mg, and I have 8.15 grams of O. Now, there's the clue. This is how you know it's a limiting reactant problem. What is it about this question that's different than the other questions we've done up to this point? Yep. There's the masses of both reactants, all right? Tomorrow, when we do the percent yield calculation, we will also be given a mass of the product so that we can do another calculation. But if you've got two reactants, it's a limiting reactant problem. So the first step is to determine which is limiting and which is excess. Just like we did with the bricks a minute ago, we're going to go to moles, all right? And we're going to head over here, and we're going to get moles, and this is going to be the moles needed. You could go the other way. There's no reason why you can't do the logic backwards. But I always just work from front to back, left to right. The second thing you're going to have to do is go down here, from here, and get the moles that you have. Because we can't just compare grams. It's all about moles. So we're going to have an extra calculation in this problem. So again, I've got to break this into three. I'm going to figure out the moles using the molar mass. You can go ahead and do that. I'm going to use a mole ratio to get me my moles needed. And I'm going to use another molar mass here to get me the moles that I have. You should be just proceeding and getting some calculations at this point. Everything's all about mass and moles except the mole ratio. Molar mass is equal to grams over moles. Choose your appropriate equation. Rustling of periodic tables. Calculate, calculate, calculate. I always get it backwards. 24.3 or 23.4? 24.3? We're looking for moles. To be honest, I don't need to see the equation. If you've got that up in the corner of your page and you're going moles is mass over molar mass and you just write down 6.73 over 24.3, that's awesome. That's fine with me. Does somebody have a number there? What do we got? Yep. 0.276. 0.276. You don't necessarily have to put it in your map if you want, unless you want. So let's use the ratio to get how many we need. We're doing this just like we've done before. There's no difference here. 0.276 on top represents the 2. X represents the 1, which means we're going to have half as much, right? It's coming down. If I bring that 1 to the other side, divide by 2, that's half. I can't do that in my head. Notice the last number in your calculator will be 0.276. You'll be staring at it in your calculator. Don't clear the calculator. Every time we do a stoichiometry problem, the number you have is going to go into the second calculation. So all you got to do here is press divide by 2, and you've got the next number. So it just builds on the next. What is that? 0.1 blah, blah, blah. I can't do that. 38? 38. So 0.138 moles needed. How much do I have? Well, I'm going grams to moles again. Same calculation. O2, 32.0 grams per mole. I need N is equal to, and I'm going to try to save some space for the last part of the question because I'm going to have to head over here. Hopefully I've got enough room without clearing the screen. I might erase. So in this case, what have I got? I've got 8.15 grams divided by 32.0. How many moles of O2 do I have? You got a number? 0.254. 0.254. 0.254. So now you have to think of the logic. Now, when you think of the logic, always start with the have in your head, because you want to compare the have to the need. If you have more than you need, excess. If you don't have enough, limited. So in your brain, you want to go have to need. I have 2.54. I need 1.38. What is this oxygen? Which type of reactant is it? It's excess, because I have more than I need. It's excess, the color doesn't matter, therefore this is limiting, and therefore I now solve the problem with the limiting reactant. Now, it doesn't matter how you solve it. The ratios all work the same. You could go back to here and build a mole ratio to get you down to here under the mg. You could also use this number, because this number comes from this number, so you could extend it across. It doesn't matter as long as you use the one that is the limiting number. If this was limiting, I'd have to use the limiting number. Okay. I'm going to try to do this on one slide, and I apologize if this is going to look a little messy. Actually, you know what I'm going to do? I'm going to erase the O2 information. You can write this next calculation down below. So I'm going to just erase as if I'm just erasing the board to make a little more room. And so I am going to go from here, earthquake, I'm going to go from here all the way over to here to these moles, and then eventually up to here to these grams, because it says find the mass of the magnesium oxide. So I'm starting with the limiting reagent number, and I'm going to build a mole ratio that brings me over to here. Okay? I'll keep writing it in blue. So that means my new mole ratio is going to be 0.276 over 2, and I'm heading over to here, x over 2. You'll notice it's a 2-to-2 ratio. It's the same ratio. How many moles am I going to have here? How many moles are we going to have? Yeah, the same as we had over there, 0.276. X is equal to 0.276. I now need a molar mass of MgO, and this time I'm going to look for the mass. MgO, 16, 24.3, 3, 4, 40.3. 40.3 grams per mole. I'm looking for a mass this time. Mass is equal to molar mass times moles. 40.3 times 0.276. Squiggle, squiggle, squiggle. And I need a number. You got a number? 11.1. 11.1 grams of MgO. Okay? All right? So it's not too bad. You're given two reactant numbers. You got to turn one into the other. I always go left to right for no particular reason. See which one's excess and which one's limiting, and then use the limiting. We will do one more. I want to do one more because this one had the limiting reactant, the first one. I want to show you a scenario where this second one is the limiting. Which number do we pick? And go from there. So I do want to show you a second variation. Sometimes I say, oh, that's good enough. Go ahead and work. But you do need to kind of see the way it looks when it's the other way around. So I've kind of given away which is the limiting, but we'll still go through the logic. But I just want you to see kind of the way it looks the other way. So again, don't wait for me. The logic is the same. It's when we get to the need and have where it's a little different. So you should be calculating away. Determine the mass of this, question mark, grams, produced when 71 grams of the ClO2 reacts with 9 grams of water, and you proceed. So this one doesn't ask you, find the limiting reactant. You have to know, hey, look, there's two numbers on the left here. Which one do I use? Right? If you're asking yourself, how do I know how to solve the products? Which one do I use? Then it's a limiting reactant problem. No, see what you just did here. I wouldn't go that way. I would go down and this way, okay? Just like I did here and here, and then I would go down here. See what we did? We went over here to find how much we need, and we went down to find how much we have. Okay? Write have right down there. Write it there, because that's super important. Yep. Have above need. Yep. So you got to find have, which is what we did there. You got to come around here and find need. Again, the map that I'm building you is built in such a way that if you do it exactly the same each time, then your logic will be fine. How do you know how to do it exactly the same each time? Practice, 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 practice. I feel like I'm a coach, chemistry coach. That practice was terrible. You call that practice? That's not practice. No, forget about it. I won't do that. Now I'm kind of in trouble here because I've kind of squished my stuff right up against here. I might have to do a little wide turn on the map. It'll work though. All right. Sure, you're finding a molar mass, ClO2, but I'm going to be kind of lazy. Sure, you're going to get that number. I'm not even going to write it in. We need to find moles. Notice it's always the same. Mass over moles. That means I need the mass 71.0 over. If someone could please tell me what the molar mass of ClO2 is. What do you got? 67.5? 67. Oh, we've got a rounding battle. Which one do we want? Libby, which one would you like? 0.5? We're going with Libby's. How many moles is that? Yep, Seth? 1.051. Lots of digits. That's okay. Extra digits is good. We'll round back. Now we've got a 6-to-3 scenario. 1.051 is 6. The unknown is 3. I bring the 3 up top there. 3 times 1.051 divided by 6. To be honest, I don't even rewrite that. In my head, I see that 3 go up to the other side. So then my calculator, I'm just doing 3 times 1.051 divided by 6. What do we have? I guess 3 down to 6 is half, isn't it? It's like a half. We're going down. What do you got? 0.525. 0.525. So I need 0.525 moles. If I have 71 grams, I'm going to need 0.525 moles of the water. Water. I got this one. 18. N is equal to 9 divided by 18. I should be able to do that in my head, shouldn't I? That's a good ratio, isn't it? 0.5? 0, 0, we'll keep the significant digits, moles, 0.500, 0.500, and now in my head, and I speak it in my brain quietly, like when I read, which is why I read so slowly, I have 0.5 moles. I need 0.525 moles. Oh my, do I have enough? No. Therefore, the water is which reactant? You're not even answering because you all know the answer, limiting. So this is the limiting reagent. I will now use the limiting reagent mole number to get me over to there, which then gets me grams. And then I finish the problem. So in this case, and I'll just change the color as I come through the have, because I don't have enough, and that's the limiting, I'm going to use the limiting number to get moles with a new mole ratio. And it looks like a 3:5 ratio, so that's kind of a funny one. And then I will head up here with a molar mass to get the mass of that final product. I have enough room to do this. I'll just do it down here. I'll do my mole ratio over here, and then I'll do my molar mass over there to the right, and I'll just keep doing it in a different color. I know you guys aren't using a different color, but that's okay. So my new mole ratio, 0.500 is the 3, X is the 5. Again, the more practice you do, the more you realize, oh, that 5 is going to go up there. 5 times 0.5 divided by 3. Don't even have to rewrite it. Let the calculator do the work. So it's 5/3. So we're going up. We're getting bigger by 5/3. I can't do that. What do you got, Seth? 0.833 moles. You don't have to write it in that spot, but that's where we're at. And now we're heading up to grams. So again, we're going the other way this time. We want mass. Mass is equal to molar mass times moles. HClO3. I'm not doing that all. You can do it. You don't know how to do that. So I just need a molar mass number to put in my equation when someone gets that number, or if they have it. Montana, what do you have for a molar mass? 84.5 grams per mole times 0.833. And what do you have for an answer for that? 70.4 grams of HClO3. All right. There's our final answer. Okay? That's a limiting reagent problem. There's a worksheet. It's got the answers on it. And then there's a few extra textbook questions. I would start with the worksheet. Again, if you can't get the balanced chemical equation, you can ask me until the class ends. And if you still can't get it, you can ask a buddy, when you're doing it for homework tonight. But practice is important. No. I was going to make I've coached. I was going to make another coaching joke. And look, in my head just moments ago, I said to myself, don't say this, because you're going to get yourself into trouble. But I can't help it. I've coached both boys hockey and girls hockey. It's a very different thing. Should I do my boys hockey coach voice or my girls hockey coach voice? Because it's very different. Well, the first one that you heard was the boys hockey coach. The girls hockey coach would go like, hey, everybody, how's it going? All right, so, hey, we've got some practicing to do. So, I think it's going to work out well. If we just work hard, I think we can pull off a stoichiometry win. All right? So let's go out there and have some fun, but make sure we practice. All right. That's the difference. Oh, and I recorded that. That's fun. You can now go back and listen to my difference between the two. Stop. I should stop recording sooner. What's the matter with me?